we have been talking about 3D viewing, right. So, let me do some of the recapitulation we did last time. So, we looked at basically the perspective projection, a single point perspective where the matrix representation of this looks like here. So, one of the entries in the last column you have it as a non-zero. So, this is when we have the center of projection lying on x axis. Right. So, a point through this transformation becomes this. This is the homogeneous part of the coordinate, and when I get the normal coordinates, the Cartesian coordinates, I divide it by this w and I get this, right, which in turn gives me the center of projection lying at this point minus 1 over p 0 0 1, and the corresponding vanishing point I get as 1 over p 0 0 1, right, and we observed how to get a vanishing point in this context, right. Take a point at infinity, apply the transformation, and whatever point you get corresponding to that is the vanishing point, right, by the definition of vanishing point itself. And then we looked at 2 point perspective, where in fact one can get 2 point perspective just by concatenating the 2 single point perspectives, and that is what is happening here. You have 1 point perspective here, this is also 1 point perspective, right, and this is the resulting transformation for 2 point perspectives, right, and this gives us correspondingly 2 center of projections and the respective vanishing points. Similarly, we can extend the idea of obtaining 3 point perspective. So, where we have all the 3 entries in the last column to be non-zero, and this is again a concatenation of the 3 individual single point perspectives, right. So, this is how we can observe the perspective transformation in the form of a matrix, single point perspective, 2 point perspective or 3 point perspective, right. And we also looked at the generation of these perspectives, right. So, how do we sensibly generate, let us say, 2 point perspective or 3 point perspective. So, which basically required a transformation prior to when you apply a single point perspective, right. So, a single rotation may give rise to a 2 point perspective, 2 rotations may give rise to 3 point perspective, right. So, these are the examples. This is a single perspective transformation, right. This is 2 point perspective and this is 3 point perspective, right. So, you can see how the parallel lines with respect to the individual axis seem to converge in all these 3 cases, right.
So, but there can be parallel lines that do not converge in the scene.
Well, see, parallel lines will converge and they may not be parallel to the coordinate axis, right. I may get, so these vanishing points which I am obtaining here are corresponding to the principal axis, the coordinate axis, right. So, there might be instances where I have parallel lines converging to a certain point, right, and these parallel lines are not parallel to the coordinate axis, right. So, those are also vanishing point, and as I said last time, we also refer to them as tracing points. Okay. And yes, there are parallel lines where this will not converge to a point in the case when will this happen? See, with respect to the projection plane, if I have a projection plane, right, and if I have lines parallel to the projection plane, what will happen? They will not converge, right. So, there will be instances where parallel lines may not converge to a point, right. Okay. So, now talking about the vanishing points, right. So, we have already seen how do we obtain vanishing point, right. So, in fact, one can do this in two ways. Let us say I am trying to locate vanishing point on the projection plane or the image plane, right. So, this is, let us say, a 3D object, and my interest is to find the vanishing points or the image of the vanishing points onto the projection plane, right. So, this is the resulting image or the projection of this object, let us say, and so the way I can obtain vanishing points, either I can look at the vanishing point to be the point of intersection of the parallel lines which have been projected here, right. So, here for instance, the vanishing point in x could be the lines which will get projected corresponding to these lines which are parallel to x axis here, which are here, these two, right. And similarly, I may get the vanishing point in z direction by taking the intersection of the lines which are the projected lines parallel to the z axis, these, right. So, that gives me the vanishing point in z. And here is the example where I have these parallel lines, right, or these parallel lines, right. They may also seem to converge at some point, right, and this may not be my principal vanishing point, but this may be some vanishing point or tracing point, right. So, a simple approach is that you take intersection of transformed lines, right, but this is computationally expensive. Since I know by definition vanishing points are nothing but the images of the points at infinity, a better way to do is take the transformation of points at infinity, right. I know the transformation which has been used for transforming this particular object. So, all I have to do is take correspondingly the points at infinity, particularly referring to the principal vanishing points, right, and just apply the transformation matrix to that, right. So, that will be computationally more efficient, right. So, now let us just do a total recapitulation of what we have seen in various kinds of transformation for 3D viewing, particularly referring to the viewing transformation, right. So, we have basically looked at two major categories of transformation, the parallel projections and perspective projection. Within parallel projection, we had orthographic projection, axonometric projection and the oblique projection, right. So, here what we observe is that the projectors are parallel, right, and depending on how we place the projection plane, we get these three kinds of parallel projection, right. So, within axonometric we have trimetric, diametric and isometric depending on the foreshortening, right. And similarly, for oblique we have the type Cavalier and Cabinet, right, and in perspective we have single point, 2 point or 3 point perspective, right. So, this gives you the overview of all the transformations we have seen with respect to viewing transformation, right. Now, one of the things which are of concern is that the implementation, and when I say implementation, I am basically referring to the interface of having this 3D viewing implemented, right. So, interface, by interface I basically mean that how would the user like to specify the various input for getting the transformation of 3D viewing, right. That is what we are looking at, and that is what is going to make your second part of the assignment. Okay. So, here what we are saying is that let us say that an object or a scene is specified in a coordinate system which I call it as word coordinate system, right. So, this is the word coordinate system where the word or the scene is specified, right. And then I have what I call it as viewing coordinate system, right. So, viewing coordinate system is that I have a notion of defining a viewer or a eye, right, or a camera. I also have a notion of defining this image plane or the viewing plane, right. So, this I would like to define in some other coordinate system, right. So, the relationship between this viewing plane and the eye is defined in another coordinate system, right, which I call it as viewing coordinate system, right. So, and this viewing plane is basically defined by, let us say, a normal to the viewing plane and the other two orthonormal coordinate axes, right. So, this is my eye coordinate system or camera coordinate system or viewing coordinate system, and this is the word coordinate system, right. So, whenever I am establishing the desired transformation for 3D viewing, I have to see that the word is specified in one coordinate system and the camera and other parameters may actually be defined in another coordinate system, right. So, there is a requirement of having the relationship between these two coordinate systems, right. Then only I can work on my scene, right.
So, why can't the eye be placed in the word coordinate system as it was done earlier?
No, yeah. So, here see what we are doing is that whenever I give these two, right. So, I am basically trying to establish the relationship of the image plane or the projection plane and the camera or the eye, right. These are interrelated. Okay. Now, given this eye somewhere, I have this coordinate system with respect to the eye, right. So, actually you can specify everything in the word, but that is not perhaps the most natural way of specifying this. So, what we are looking at is what is the convenient way of specifying these. Okay. So, another thing is that this word coordinate system is actually a right handed system, as you observe here, whereas here when I see the eye coordinate system, it is left handed system. This is also for the matter of convenience, right. I have a convention that let us say the line of sight which is going from the eye towards the scene, right, corresponds to the n axis. This is just a convention. So, that makes this coordinate system right left hand coordinate system, right. So, once we have seen this, so let us try to look at individually what we require for specifying the various entities in these two coordinate systems. So, in viewing coordinate system, I need to have the position and orientation of the viewing plane, right. Where do I locate the viewing plane? That is important, right. And then the extent of the viewing plane, that defines the window where I want to capture the projection of the image, right, projection of the scene as the image, and then position of the eye. right. That basically takes care of having the viewing coordinate system defined. Now, considering viewing plane or the view plane, what I have is a view reference point, I call it as VRP, which can act as the origin of the viewing coordinate system, right, and that may be specified as, let us say, Rx, Ry, Rz in word coordinate system. So, this VRP, which is the viewing reference point, is some sort of a is an offset with respect to the origin of the word coordinate system, which locates the viewing plane, right, or the origin of the viewing coordinate system. Now, this could be actually given as the center of the scene. I can consider as, let us say, the center of the scene to be the VRP, or it could be any point defined by the user, right. So, all what VRP is doing is actually telling you that where is the origin of the viewing coordinate system with respect to the origin of the word coordinate system, right. And let us say the normal to the view plane is defined by the vector n, nx, ny, nz. Right. This is the normal to the viewing plane. So, that basically locates the viewing plane. Now, for defining the normal direction, there could be various ways, right. One can actually define a vector and say that this is the normal of the viewing plane, right. But there could be other ways which are thought to be more, let us say, intuitive and convenient. So, if you consider in spherical coordinates, so what we are saying is that a vector r, right, in this spherical coordinate system could actually be defined as the normal vector, right, where r is defined in terms of theta and phi. Right. So, what you are saying is that there is a sphere in the word and you are locating the normal of the viewing plane somewhere in the sphere, right. So, that could be one way of looking at defining this normal vector, right. So, here I get this normal vector as this. So, this is a unit normal vector, right. One could also define the normal vector as just as minus r, where r is my offset for VRP, right. If I locate the view reference point, then my normal could just be defined as minus r, right. So, there are various ways in which you can define this normal. Okay. So, this is the prerogative of the user, how the user wants to define it. So, you are just giving the interface or the facility for the user to define this normal, right. Okay. So, we have basically looked at that how do we define the viewing plane. So, the other corresponding entities with respect to the viewing plane can actually be derived. So, there is one, let us say now what we are left with defining with respect to the viewing coordinate system are the two other orthonormal vectors, the u and the v, right. Now, as far as the direction v is concerned, we try to capture the vector v something which matches to the notion of an up vector, right. So, whenever we look at a scene, we have a notion of what is the up vector, right. So, in this room, for instance, when we are looking at, we have the notion that yes, this is my up vector, right. If I go upside down, then I have some other up vector. right. So, there is a notion of up vector. So, what we try to do is we try to basically capture that up vector in the definition of v direction. Okay. So, what we are saying is that let us say this up vector be defined by the user in Word, and we would try to take that information of up vector and define the corresponding v vector. Okay. So, let us say this is the up vector defined, right. Then I can define the v vector just taking as, so if I take the projection of this up vector, this is in the direction of the n vector, right, then I am interested in getting this vector, right. So, these are basically related as the up prime, which is the projection along the n vector, is equal to up, sorry, this is the up vector prime, this is the up vector prime, right. And so, what I have is this is given as the up dot n in the direction of n, right, this vector, and this is my up vector. So, this is the up prime vector, which corresponds to what I want to fix as the v vector. So, I just normalize that dividing by the magnitude of this, and I get the unit v, right. So, that gives me the direction for v. Once I fix the vector v, I can get the direction u just by taking the cross product, and we have to account for that. Since the system is left handed, I would take n cross v, right. So, this basically fixes the three directions I needed for the Wing coordinate system and the location of its origin, which is defined by the VRP. Is it okay? So, now the window, which is the extent of the viewing plane or the image plane, can just be defined as the extent in terms of the left extent, the right extent, the bottom extent and the top extent, right. So, WL, WR, WB and WT. So, this is just the extent of the plane, right. And the I now, which could be located in this coordinate system, I am referring to the viewing coordinate system also as let us say UVN system, right. So, where this E could be located as EU, EV, EN in this coordinate system, right. So, this is E located in this coordinate system. Now, typically we observe that I is actually defined in such a way that it coincides with the normal of the viewing plane, right. So, line of sight is actually the normal of the viewing plane. Okay. Now, the other thing is, now what has happened is I have basically defined a viewing coordinate system. I have the word defined in word coordinate system, right. Now, what do I need is some mechanism by which I can make a transformation from one system to the other system, right. That is what I need. So, in order to do that, let us try to see a simpler case in a 2D, when I need to make this transformation from one coordinate system to another coordinate system, right. So, let us say I had this coordinate system where I had these x and y axis, and the other coordinate system defined by u and v, right. So, a point located here x y can be related to the point in this coordinate system, which could be given as a and b, right, using this, where r is the offset between O and O prime, right. And if I define u v as just my matrix of transformation, right. So, I get x y as a transformation of a b through m and r, right, because u v is nothing but a transformation of the unit vectors, let us say 1 0 and 0 1, right. So, I am basically saying that u v is equal to 1 0 0 1 transformed by m. Therefore, m is nothing but u v. You get that? So, now I have the relationship of the two representations of the same point in the two coordinate systems, right. So, this was in 2D, now this I can also do in 3D, right. So, this m is nothing but basically the unit vectors in the other coordinate system, right. So, now in our context what I have is, let us say, the point a b c in the viewing coordinate system, x y z in the word coordinate system, right, and this m is nothing but, now instead of just having u v, I have u v n, right. So, this matrix gives me the transformation m, right. So, now this point P defined, let us say, in word by x y z is related through the matrix M and the offset distance r with A B C, and now I can get A B C from the point in the word, right. And remember that this matrix is actually is an orthogonal matrix, because it is going to be a combination of rotations, nothing more than that, right. So, the inverse of this matrix is given by the transpose of this matrix, right. So, I basically have A B C related to the point P in word as x y z through this, right. And I can also write this in terms of the 3 dot products if I want, right. So, P minus r dot u, P minus r dot v and P minus r dot n. So, let us say if I now represent this in homogeneous coordinates. So, that is what we deal with. We have these transformations represented in the homogeneous coordinates. So, A B C 1 is obtained from the word coordinate system point x y z, let us say, through a matrix A from word to viewing. Okay. So, now A W V is nothing but a matrix consisting of the transpose of M and plus some other terms which could be for the translation, right. So, this submatrix, the 3 by 3 submatrix here, is nothing but the transpose of M. Now, if I go back and see the exact form of A B C from the point P, I have this, right, so which I just rearrange and get a term what gives me the translation, right. So, this is nothing but the transformation of the point P through the matrix M T, and this is the term which is accounting for the translation, right. So, I just look at this, which is nothing but the r getting transformed by m t, and which I can let us say write as r x prime, r y prime and r z prime. So, these are the three translations corresponding to this, right. So, now the point in u v n or viewing coordinate system is related to the point p in the word as x y z by this matrix A w v, where A w v is given by this, right. So, these are the translation terms added now, and this is nothing but the column vectors of the unit vectors in the viewing coordinate system, right. So, I can basically derive a procedure of converting the point in the viewing coordinate system and the point in the word coordinate system. So, I can go either way, from word to the viewing coordinate system or viewing coordinate system to the word through this, right.
Can you repeat what R?
What is R?
Origin of the.
So, R is the VRP. Remember that we have defined this view reference point. So, it is nothing but the offset vector between the origin of the word coordinate system and the viewing coordinate system. It is basically locating the origin of the viewing coordinate system, right. Okay. So, now let us try to see in a geometrical sense, which we also did in the perspective transformation. So, what is basically happening now? I have a point P given in the viewing coordinate system through, let us say, P u, P v, P n. This is my viewing plane, right, and this is the I, right. So, I get the projected point, let us say P star on this viewing plane, right, and I am defining, let us say, the viewing plane at n equals to 0, right. So, the third coordinate is 0 here. So, I am having basically the coordinates as u star and v star, right. So, now if I consider this is nothing but a ray emanating from the point E, which is the I point in the word. Now, the word is now in viewing coordinate system. I have already obtained, let us say, this point in the viewing coordinate system, that I can do now, right. So, I can define this ray from E to P, right, and P star is some point on this line or on this ray, right, at some t is equal to t prime, right. So, if I take the parametric definition of the ray or the line, so this r is not the same r which we had seen, that r was a vector r, distance from the word coordinate system. So, this is just I am representing as the ray, parametric ray, right. So, now this can be basically written as parametrically like this, and if I am interested in finding out T star, all I am saying is that on u v plane, where I consider n equals to 0, I have this r t at n is equal to 0 given as this, right. So, this gives me the t prime corresponding to the point on the viewing plane, right. And now, by substituting this t prime, I can get u star and v star, right. So, these are my transformed points u prime and u star and v star, right. Now, let us say I further simplify and say that I is located such that this E u and E v equals to 0. That means, I is direction is coincident to the normal vector, right. In that case, I observe that u star becomes this p u over E n minus p n, and similarly v star becomes p v over E n minus p n, right. So, this rings a bell, right. We have seen such a thing, right. In fact, I can write this as nothing but in a matrix form like this. So, this is 1 over E n, right, and this is nothing but actually a perspective projection, single point perspective projection, right. And the corresponding matrix for perspective transformation, single point perspective transformation, is this, right. So, all I am saying is that I have this transformation which is happening through this matrix, right, provided the I is on n axis, right. That is what I am assuming. So, next let us say, so all which is being said here is that if I use this perspective transformation given through the matrix M p, right, to get the points on the projection plane as u star, v star, n star in general, right. So, this n star is let us say not 0, because it does not actually change anything, right. Then I have the u star, v star and n star given as this, right, and this n star is actually capturing the depth information, which is important when we will talk about hidden surface elimination. Right. So, even after having applied the perspective transformation, we need a mechanism by which we can order the depth such that the points which are farther, and if they are occluded by the points in front, they are not shown, right. So, that would be obtained using information from this third coordinate. Okay. So, the relevance of this will be clearer when we talk about hidden surface elimination. Okay. So, what we have basically established that there is a matrix M p which is giving us a transformation to get the point on the projection plane, and that we have seen earlier also. So, there is nothing very new in it, right. But within the interface which we are specifying, how we can obtain the big matrix A W V, that is what we are trying to see. Okay. Now, let us say I relax this condition where I had considered the I lying on the n axis, right. So, let us say if I have the I lying off n axis. Okay. So, what happens is that I would get another matrix, remember we had seen this earlier, is this u star, v star coming as this, right. So, now I want to capture this through a matrix, that is all I am doing, right. So, now basically I observe that there is an additional matrix which I need before I apply the matrix M p, right. So, that is an easy exercise for you to figure out that corresponding to the points we have obtained u star, v star, a matrix of this nature can be obtained, right. So, what is this saying? What kind of transformation is it saying? Just looking at the matrix itself, can you suggest what kind of transformation it would be with these terms here? Shear. So, there are terms in the off diagonal, right. So, this would cause some sort of a shear, right. So, what we are saying is that this point P star, after the matrix transformation, let us say this M s and the transformation matrix M p, right, will give me the point transformed when I consider I not to be coincident with the n axis, right. So, more general case. So, if I have a point Q in the word coordinate system, it will map to P star through this, right. So, AWV was nothing but the transformation from word to viewing, right. That is where we had defined the point in viewing coordinate system, and after that we had further applied these two transformations, right. Okay. So, now what have we basically achieved? We have everything in a coordinate system like this, right, where I have the I, the viewing plane. So, what I basically define is some sort of a volume within the coordinate system, right. Remember that this viewing plane actually has got extents, right. So, if I just join the point I and emanate a ray from the extent of the window, I will basically get some sort of a volume. If I also define certain planes to clip this volume in the n direction, right, direction towards the line of sight, right. So, all I am saying is that I can actually put the scene in this view volume. This is also necessary and important, that whatever scene gets intercepted within this volume is of interest, right, and that is where your clipping comes, right. I can also perform clipping of the scene with respect to this volume, right. So, whatever gets intercepted here will be of interest, right. So, let us say I define the two planes or the extents in the direction of or towards the line of sight, right. So, there could be two planes defining the front plane and the back plane. So, all is it saying that this is front of the viewing plane here and this is the back of the viewing plane, right. So, just to give the extent in the depth which I am interested in, fine. So, now having seen this viewing volume, now if we just look at the location of the front plane and the back plane, right, in let us say the direction n, and let us say I am just taking a slice of that, then I see that the front plane is located let us say at f and the back plane is located at b in n direction. Okay. Now, so what has been achieved, that after having transformed from let us say the word to view, I would get something like this, right, and these are my window extents W b and W t in v direction, right. Now, what happens when I apply the matrices like M s and M p? Right. So, remember that if I have the point at a distance f in n direction, we will actually get mapped to something like this, right. Similarly, a point b in n direction will actually get mapped to something like this, right. Are you convinced? No. So, let us go back and see, we have already, it is right there actually. Right. So, now all I am saying is that I am looking at only the points in n direction, right. So, it is located at f. So, this f will basically will get mapped to this, and this b will get mapped to this, right. Now, so what is basically being achieved is some sort of a distortion or a warping of this volume into this, and that is what we obtain from the perspective transformation. See, perspective transformation is basically some sort of a distortion or a warping. So, a scene like this would actually appear to you like this, right. So, this whole thing is a matter of a warping or a distortion, right. So, let us try to see a little more of this. Now, what I have done is I have applied A W V, right. From there I applied the other matrices M s and P to get to this situation, right. Now, what I do is I basically put this volume or make this volume normalized. What do I mean by normalized volume? I just define an extent of this volume for the directions u and v, let us say using V L, V R and V B, V T, and the depth between 0 and 1, right. So, the depth is basically normalized between 0 and 1. So, this is I am giving you an example where the normalization is done between 0 and 1, but in many cases the normalization is done between -1 and 1, right. So, for instance, OpenGL does between -1 and 1, but that does not change anything, it does not change anything, right. So, let us say now what I want to do is, after having obtained the distortion or the distorted volume, I want to map that to this normalized volume. Okay. So, how do I do that? So, just consider for the part using coordinate n. Okay. Now, this was my front plane, this was my back plane, right. Now, I want to map this to something like this. This maps to 0 and this maps to 1, right. So, any point just for the part n, right, just consider the part n, let us say n o, which is the original n, gets mapped to something I call it as n transformed, right. So, this is just a linear ratio which I am considering for the transformation, right. So, all I am saying is that if I want to locate n t within this, I can locate through using the ratio of n 0 within this, right. So, n 0 minus this divided by the whole length, that locates NT. Right. So, what I observe is that with respect to N0, I have this part as which is acting like a scaling to the N0, and there is some translation. Right. So, I am just decomposing that to be a transformation in terms of scaling and translation. Right. So, once I do this, I can actually form a matrix N which will do the normalization in all the three directions. So, this was done only in N direction, similar treatment can be done in other directions U and V, and I can obtain a matrix of this nature in a very similar way, right, just using the ratios. That's all I am doing. So, this these values Sn, Sv and Su, Sv and Sn and Ru, Rv and Rn are basically given here, right, derived in a very similar way. So, I get a total transformation which looks like this, from the word to the normalized volume. Right, basically given like this, and once I specify the input in terms of where the I is located, what is the N, what is the view reference point, I can actually establish this. What is the extent of the window, right. So, your assignment is going to be based on this, where the user is going to specify those parameters and you will achieve this. Okay. So, this basically gives you the entire viewing transformation pipeline. Is it okay? So, next time we will start on something else. So, that basically takes care of the viewing transformation. Right. And once you do this, you can actually get your clipping done in this pipeline. Right. So, you can actually do, instead of 2D clipping, you can do 3D clipping. And now the question comes, is it better to do 2D clipping or is it better to do a 3D clipping? Anyway, that is a question for the minor. Okay, thank you.